This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into the research paper, OK Robot, What Really Matters in Integrating Open Knowledge Models for Robotics. This paper presents a novel framework for pick-and-place robotic tasks using open knowledge models. Let's start with the core problem the authors are addressing. What are the limitations of current robotic systems that OK Robot aims to overcome?
Current robotic systems often suffer from brittleness and poor generalization. They struggle in unseen environments and with objects not encountered during training. Even large data-driven models often fail when faced with the variability and complexity of real-world unstructured environments like homes. OK Robot attempts to address this by leveraging pre-trained models trained on large public datasets, avoiding the need for extensive robot-specific training.
The paper highlights the surprising underperformance of systems combining advanced vision models with established robotic primitives. What are the key challenges that contribute to this underperformance?
It's not a single challenge, but rather a compounding of inaccuracies across different components. Inaccuracies in object retrieval from language queries, navigation targets that are unreachable or unsafe for the robot, and variations in grasping model performance all contribute to a significant drop in overall success rate. The paper argues that a nuanced framework is needed to effectively integrate these components.
OK Robot adopts a systems-first approach. Can you describe the architecture and the key components of this framework?
Okay, Robot integrates three primary subsystems: an open vocabulary object navigation module, an open vocabulary RGBD grasping module, and a dropping heuristic. It uses pre-trained vision language models, VLMs, like CLIP and OWLVIT for object detection and localization, navigation primitives for movement planning, and grasping primitives for object manipulation. The system operates in a sequential manner, moving from object localization to navigation, grasping, and finally dropping the object.
The paper mentions the use of a voxel map for object-centric semantic memory. How does this component work, and what are its advantages and limitations?
The voxel map is a 3D representation of the environment built from a manual scan using an iPhone. It stores CLIP embeddings associated with each voxel, providing a semantic representation of the scene. Advantages include relatively low resolution compared to prior work, allowing for tolerance of small object movements. However, a significant limitation is its static nature. It doesn't adapt to changes in the environment during the robot's operation.
The navigation module seems crucial. How does OK Robot handle navigation to the target object, considering the need for proximity, for manipulation, and obstacle avoidance?
OK Robot uses a weighted-a-star algorithm for path planning, incorporating 3 score functions to balance proximity to the object, sufficient space for manipulation, and obstacle avoidance. The algorithm generates paths that are similar to ideal Voronoi paths, minimizing the risk of collisions.
The grasping module utilizes any grasp. How does this model work, and how are grasps filtered and selected?
Any grasp generates collision-free grasp poses from a single RGBD image. These grasps are then filtered using LangSam, which segments the image and identifies the object mask based on a language query. A heuristic is applied to select the best grasp, balancing graspness score and grasp orientation, favoring horizontal grasps for robustness.
The paper reports a 58.5% success rate in unseen, cluttered home environments, increasing to 82% in cleaner environments. What are the key factors contributing to this performance difference?
The difference is largely attributed to the naturalness of the environment. Clutter, ambiguous object queries, and objects with challenging physical properties, for example, too large, slippery, or translucent, significantly impact performance. The higher success rate in cleaner environments demonstrates the sensitivity of the system to these factors.
The paper conducts ablation studies comparing different semantic memory and grasping modules. What were the key findings of these experiments?
The ablation studies showed that voxel map performed comparably to other semantic memory modules with lower variance, indicating higher reliability. Any grasp significantly outperformed other grasping methods, highlighting its robustness. However, the fact that a simpler heuristic-based method performed better than some other pre-trained models underscores the ongoing challenges in developing truly general-purpose grasping models.
The authors analyzed failure modes in detail. What were the most frequent causes of failure in the home experiments?
The most frequent failures stemmed from issues with object retrieval from semantic memory due to ambiguous queries, 9.3%, difficulties with grasp, pose generation and execution, 8%, and robot hardware limitations, 7.5%.
Can you elaborate on the challenges related to natural language queries and their impact on the system's performance?
The performance of the VLM-based object retrieval is sensitive to the wording of the queries. Slight variations in phrasing can lead to different results, highlighting the need for more robust and less ambiguous language processing. An interactive system allowing user confirmation could mitigate this issue.
What were the main limitations of the grasping module, and how could these be addressed in future work?
The grasping module relies on a single RGBD view and a model not specifically designed for the robot's gripper. This leads to unreliable or infeasible grasps, collisions with obstacles, and difficulties with certain object types, for example, flat objects. Generating grasp plans instead of just poses and using models trained for the specific robot could improve performance.
The paper also discusses robot hardware limitations. What are some of these limitations, and how might they be overcome?
Limitations include payload capacity, arm reach, hand-eye calibration issues, and wheel limitations on different surfaces. More robust hardware with increased payload capacity, longer reach, improved sensors, and better locomotion would significantly enhance the system's capabilities.
Finally, what are some of the key open problems and directions for future research identified in the paper?
Future research should focus on developing dynamic semantic memory and obstacle maps that adapt to changes in the environment, generating grasp plans instead of just poses, improving the interactivity between the robot and the user to handle ambiguous queries, and implementing robust error detection and recovery mechanisms are also crucial areas for improvement. Robustifying the robot hardware itself is also a key area for future work. This has been a comprehensive discussion of the OK Robot paper. Thank you for your insights.